And we'll be doing this again next week here, where one of our very own professors, Dr. Ann Bykirk-Kaufman, will be giving a talk on her research the last 30 years in the Coyote Mountains. But today we are very fortunate to have Dr. Tomoko Komada from San Francisco State University. Dr. Komada received her PhD in 2002 from Rutgers, the State University of New Jersey. I think that's the official name. And also a master's at Rutgers, and before that, a Bachelor of Arts in Chemistry at International Christian University in Tokyo. Dr. Komada is a leader in 2 labs at San Francisco State University, the Komada Biogeochemistry Lab. They're interested in biogeochemical processes that transform organic matter into marine sediments. And also with the Estuary and Ocean Science Center at SF State's Romberg-Tiburon campus, where they're very interested in solutions to environmental problems that affect coastal communities. So we're very fortunate to have Dr. Komada here. She came to Chico purely through public transportation from San Francisco State all the way here, and we're headed back. So that's great to see. You're almost always. Okay, almost. And is also moving into a new building similar to this at San Francisco State very soon. So it's also noticing the facilities here and try to give you a tour as well. So with that, I'll give it to Dr. Komada, and thank you for being here.
Thank you for that lovely introduction, and thank you for the kind invitation. Thank you for the hospitality and the so I tried to make it 100% public transportation, but in order to do that, I would have had to leave yesterday. So I did drive the first 20 minutes, 30 minutes, I drove to the Amtrak. So with that. So let's see. So I've been doing research for almost 3 decades now, and my research focus has always been in carbon cycling in sediments in offshore marine systems. But starting about 6-7 years ago, I think, I started to be more interested in carbon cycling in nearshore systems, and today we're going to be focusing on salt marshes. And the whole reason I got interested was the discussion surrounding blue carbon. Can you raise your hand if you've heard of blue carbon? Oh. Okay.
The oceanographer, lovely.
So this really changes from group to group. So blue carbon is very simple. It's the most simple definition is organic carbon that is stored within coastal vegetated habitats, such as mangrove forests, eelgrass beds, marshes. Nowadays, kelp forests tend to get pulled in as well, although they function slightly differently. So the reason why blue carbon ecosystems have gotten a lot of interest is that they tend to accrete sediment at a pretty fast rate. And if you measure the carbon content, you find that there's quite a bit of carbon in there. So the idea is that fast rate of carbon burial, accretion, means more CO2 drawdown from the atmosphere, therefore mitigating climate change. So there's a lot of interest in managing blue carbon ecosystems as a means to mitigate climate change. And there's a lot of programs looking to give carbon credits to people who manage blue carbon systems. So today, what I'm going to talk about is not how blue carbon ecosystems might save us from global warming. It's more about highlighting the complexity of carbon cycling in systems like salt marshes, and also to highlight the fact that if we equate carbon burial to CO2 drawdown from our present-day atmosphere, if we do that, we may end up going down the wrong path as far as climate mitigation goes. So this work was done with an army of undergraduate students. So Anthony Bravo, Kevin Liu, Lily Wong, Cameron Shields, Andres Viva, us, they've long since graduated, and one graduate student, master's candidate, Mandy, and myself. So they're all co-authors except for Andres, who left fairly early on in the project. And I also thank the marsh experts, because I knew nothing about marshes. They're way more dynamic than I had ever imagined. So without them, I would not have known where to go, how to sample, and all of that. So I acknowledge them. And then funding was from the American Chemical Society Petroleum Research Fund. Okay, so I'm going to start with a few terminology. So I'm going to be using the OC as a shorthand for organic carbon. And organic carbon is going to be either autochthonous or allochthonous. So autochthonous, if we're talking about salt marsh systems today, so organic carbon that is autochthonous would be carbon that is photosynthesized within the marsh by marsh plants, whereas allochthonous carbon would be carbon that's imported to the marsh, so it's photosynthesized somewhere else and then transported in. Today's talk is going to focus on what we call minerogenic marshes as opposed to peaty organogenic marshes. So peats would be just 100% biomass. So whatever plants that were growing there, they die, and then that's what's accumulating. Whereas hydromarshes like these, there's mineral veins as well that get imported. Okay, so all of what I'm going to talk about has already been published. It came out in a special issue 2022 in Limnology and Oceanography. So now that you had your snack, you can just go and read this instead. But if you prefer the live version, you can stick it around. All right. So again, the motivation to study salt marshes again is that they're very productive. They grow really fast, and when they photosynthesize, they take CO2 out of the air, and and then organic carbon is deposited. Okay, but tidal marshes, minerogenic marshes are all tidal marshes. So what happens with these? Take a step back. So the idea again is that they are taking CO2 out of the air. So the idea is that this is offsetting some of the CO2 that you and I emit. Okay? But the thing about these tidal marshes, minerogenic marshes, is that they also import material from outside systems, including upland terrestrial ecosystems. Okay, so but then you're like, well, so who cares? If this is still offsetting anthropogenic CO2 emissions, this is still good because we're sequestering that. But the thing about upland terrestrial soils, the systems, is that there's a lot of carbon storage in soils where carbon can age for centuries to millennia, and this old material is also subject to erosion, transport, and deposition at the marsh. So this ancient material that was photosynthesized, way back when, centuries to thousands of years ago, has that deposition of that material in the marsh has nothing to do with ongoing, you're not offsetting CO2 emissions at all. But this point is not surprisingly appreciated in the literature at all. And I'll cite one other study that actually talks about this, but the vast majority of the papers out there do not acknowledge this possibility. So we wanted to know what are the sources of organic carbon to marsh sediments, how much of it is locally produced, how much of it is imported, and how much of it is old material. And then another question we looked at is what is preserved in the long run. So, so material that is deposited at the marsh surface undergo burial, and there's bioturbation, there's tidal exchange, there's microbial or macrofaunal respiration, there's a lot that goes on. So it doesn't mean that whatever is deposited at the surface is going to survive burial over the long term. Another point that is not really appreciated in the literature, the thinking is changing a little bit now, but still not enough in my opinion. So how do we go about addressing these questions? We took two approaches. Is that a hand up?
No.
Oh, okay. So just if anyone has a question, please raise your hand. So I love isotopes. I'm a carbon isotope person. So I'm looking for problems where carbon isotopes definitely one of them. Okay, so carbon comes in 3 flavors. There's carbon 12, 13, and 14. 12 and 13 are stable isotopes, and then 14 is a radioactive isotope. C14 is present at trace levels, C13 about 1%, and the vast majority is carbon 12. So looking at the C13 to 12 ratio is really useful in getting an idea of how the organic carbon was created. Okay, so what do we mean by that? So most of the terrestrial ecosystem, the plants in the terrestrial ecosystem carry out photosynthesis through what's called a C3 pathway, whereas the low part of the marsh, where Spartina, which is a California cordgrass, dominates. So California cordgrass carries out photosynthesis through what's called a C4 pathway. And what's interesting about this is that they fractionate carbon isotopes differently. So the end product is that the 13 to 12 ratios are different for C4 biomass versus C3 biomass. So the C3 biomass has lower C13 to 12 ratio compared to C13 to 12 ratio in C4 biomass. So the ratios, the actual ratios, we report as compared in reference to a standard material. And by the time we've done that measurement and converted the units, we report in lowercase delta notation. Okay, so in delta C13 units, C4 plants tend to have C13 signatures somewhere like minus 14, minus 15 per mil, whereas most trees out there would have a C13 signature of somewhere around minus 27 per mil. So they're very, very much different. Okay, so then how about the age? Okay, how about the age? So this is where radiocarbon comes in very handy. So radiocarbon is radioactive and it ticks with a half-life of 5,730 years. So it's very useful to look at carbon cycle processes that take place on the time scale of centuries to millennia. So then, let's see. We report radiocarbon abundances purely as a clock. So any fractionation effects have been normalized out. So C14 abundances we use purely as how long the material has been cut off from the atmosphere. But through convention, it so happens that by definition, the radiocarbon value of CO2 in the atmosphere today is right around 0 per mil. So how many of you know about radiocarbon signatures in the atmosphere? Okay, so I think many of you may know about the bomb signal. So it shot up to like plus 1,000 per mil, but then it's been coming down. And nowadays, I think starting about last year, it hit 0 again, somewhere close to 0. So we're very close to 0. Okay. So if any plants that are alive and exchanging carbon with the atmosphere will also have C14 signatures close to about 0. And you and I, because you're eating and we're alive, unless you're like to suck up coal or something, we're going to have C14 signatures very similar to the atmosphere. Okay, and then so just as a reference point, if you let organic carbon carried away from the atmosphere, let it age for maybe 1,000 years, C14 signature would decline to maybe negative 1,000 per mil, something like that. And if you take petroleum or anything older than 60,000 years, you would have a delta C14 value of negative 1,000. So no longer detectable. C14 is no longer detectable. Okay, so approach number 2. So in addition to doing isotopic measurements, we avoided doing, well, you can do isotopic measurements on the bulk sediment, but sediments are very heterogeneous, and you guys know there's a lot going on. There are different parts in a small sediment sample. So another thing we did was to oops, sorry, hitting the wrong button. So another thing we did was to density fractionate. So we took the mud and then we density fractionated it to high density and low density material. But separate out organic material that is physically tightly associated with mineral high density particles to organic material that's free floating by itself. So what do we mean by mineral bound or mineral associated organic matter? So if you look at sediment particles, so these are examples from river and estuarine and marine sediment. So you find what's called organo-mineral complexes. So if we take if we zoom in further, these are images of, so this is clay-rich soil, marine sediment, and so this dark area, that's clay particles, and then here's a polysaccharide right next to it, and then here's a bacterial cell, and then over here we see similar sort of close associations between organics and inorganic components. So these associations have been shown to be pretty strong, and they don't form instantaneously. They seem to form over time. So by doing this density fractionation, why we did this is that it helps to, helps distinguish autochthonous versus allochthonous organic carbon. Because at the time of deposition, if the organic material is already tightly associated with minerals, then it has to be allochthonous because it doesn't form right away. Whereas autochthonous carbon should be mineral-free at the time of deposition. And another reason to do this is that there's a very rich body of literature out there going from terrestrial soils all the way to marine sediments about the fact that organic material that is associated with minerals withstand degradation in the environment over a longer time period than organic material that are on their own. They tend to degrade faster. So it helps sort organic carbon according to expected longevity in the environment. So if you are autochthonous carbon produced right here in the marsh, we hypothesize that the best way to withstand burial and survive is to become associated with minerals. So another question we asked is autochthonous carbon incorporated into the mineral boundary? So here are the questions. So what supplies organic carbon to these sediments? Question number 2, to what extent is autochthonous carbon incorporated into the sediment matrix? And we looked at this 2 ways. Is it incorporated into do we see incorporation at the bulk sediment level? And then is there evidence for incorporation specifically as a mineral bound pool? And how stable is autochthonous carbon in the long term? Okay, so sample collection and processing. This was really fun. So you don't have to go on a boat, which is very convenient. So we hit 2 sites in San Francisco Bay. The Estuary and Ocean Science Center is right here on the Tiburon Peninsula. SFSU campus is down here, so I commute back and forth. My lab is at the Estuary Ocean Science Center. So we went to 2 sites, Chinatown, actually very close to Chinatown, and also Lombard Point. So this is Marina Street, Chinatown Corporation is over here somewhere. So we picked these 2 sites again based on the input we got from the marsh gurus, and they told us that these are just about the only historic sites that have not undergone restoration. So I wanted a marsh that's been around for a really long time, and they said that's really hard to find. So we could only go back maybe like a century by coring. So we sampled these sites in 2016 and 2018. Okay, we sampled at each site. We sampled the Spartina zone, so this is a low marsh area, and also the right next to it in the adjacent mudflat as a control. So we wanted to see the effects of having the plants there as opposed to not. Okay. And then we used a handheld Russian heat borer. So the cores are about 50 centimeters long, 5 centimeters in diameter, and then based on the sedimentation rate that's published for this for the entire bay, we estimate 50 centimeters to cover maybe 130 years of sediment accumulation. And then we cores right there on site, and then we drove right back to the lab, and then we gently pushed each interval through a 2 millimeter sieve. So no water used, just gently pushing the mud through, and whatever that we captured on the sieve, we called it detritus, and these were rinsed and then dried and then later analyzed for both carbon and stable isotope signatures. And then the material that passed through the sieve, this is what we call bulk sediment. I'm going to be referring to this as bulk sediment. I'm using a circle to indicate that. And then so it's easy to see. So this is also the fraction that we subjected to density fractionation, which I'll tell you about in a bit. Okay. So at the bulk level, again, we looked at the carbon content and then the stable isotope and radiocarbon values. So, so I have other slides for this, but in the interest of time, I'm just going to tell you that in terms of carbon content for the whole sediment, the detrital carbon, organic carbon contributed by the detrital material was minor compared to the amorphous brown stuff. So the amorphous brown stuff was the biggest carbon pool. Okay, so in the next few slides, I'm going to show you the isotopic composition of the box sediment and the detritus in relation to the isotopic value of the live roots. Okay. All right, so I'm going to show you those in order to address the first question, which is what supplies organic carbon to these sediments. All right, so I'm going to go over here. All right, so this is easy. So we have, let's see, I have Gallinas Creek, and then I have Dumbarton Point. Okay, so I'm showing results for the Spartina zone only. We have sediment depth going down 50 centimeters, and then the x-axis is delta C13 signature. Okay, so the green crosses. These are the isotopic signatures we got for the live roots that we pulled out right after we poured. And then the stars are the detrital material. So if you see different styles of the same shape, that means replicate cores. So for Dumbarton Point, we only got 1 core, but for Gallinas Creek, I think we got 3 cores. So you can see that the C13 signatures of the detritus very much overlap the C13 values reported for Spartina, the photographs in San Francisco Bay. So this says that the detrital material very much looks autochthonous. And in comparison, the circles here now are the bulk sediment signatures. Okay, so there's a big shift there. It's a lot more depleted, and these values also overlap with estuary marine ceston. So can you raise your hand if you're okay with the word ceston? Okay. So ceston is anything particles that are floating, suspended in I think we usually use this in an estuary context. So if you take estuary sample, water sample, and you filter it, and you got some particles, that's it. So it doesn't have to be alive, dead, anything that's floating, that's ceston. Okay, so it overlaps with estuary ceston, but it also overlaps with estuary phytoplankton. I guess there's a lot of C13 values reported for San Francisco Bay, marine estuary phytoplankton, and also overlaps with benthic diatoms. Okay, but we discount diatoms and phytoplankton because of the following reason. So now we're looking at radiocarbon. Okay, so here's 0. So positive. So right around here is modern, present day. Anything positive has the bomb signal in it. So maybe like within the past decade, few decades or so, and then getting older to the left. Okay. So we did not do radiocarbon on roots because radiocarbon measurements are kind of expensive, and we knew that they were alive, so we skipped on that one. But compared to what's expected for roots, the bulk sediment delta 14C values were a lot lower, -100 to maybe -200 per mil. And this difference is significant, and it's not due to aging 2,730 years. So this offset is more like 1,000 years, 2,000 years. Okay. So based on this, the low delta C13 and delta 14 C values in bulk sediment indicate presence of allochthonous organic carbon that has undergone aging prior to deposition in the marsh. Okay. So that's our first. Okay, so here. Question 1: what supplies OC to these sediments? So local cordgrass is the dominant source of organic detrital material. So those are the little stars, stuff that got caught in the mesh. And then, but at the bulk level, so the homogeneous amorphous brown stuff, there's a preponderance of allochthonous, so imported organic carbon that looks like it's gone aging prior to entering the mesh. Okay, so moving on to question number 2. What extent is autochthonous carbon incorporated into the sediment matrix? So we'll look at this at the bulk level first. So, oops, sorry, not getting used to this. Okay, so we have Galenas Creek in red, okay, Dunbar Point in blue, and I'm going to plot the Spartina zone data at the top, and then the mudflat data at the bottom, and the mudflat symbols are going to be open, and then the Spartina zone symbols are going to be filled. And again, different flavors, different styles of the same shape being replicate course. And the dashed lines indicate the average in the mudflat. So we're looking at carbon content, organic carbon content here. So we see that the carbon content is a little bit higher in the Spartina zone compared to the mudflat at both stations. And then if you look at C13 signatures, again, a little bit higher for in the Spartina zone compared to the mudflat. Definitely in Galenas Creek. Dunbar Point maybe a little bit. And if you look at radiocarbon, again, a little more to the right. So this is actually huge, almost 100 per mil, and that's a gigantic difference. So yeah, definitely more positive in the Spartina zone compared to the mudflat right next to it. So just looking at the values this way, it looks like based on the isotopic signatures and organic carbon content, they're consistent with greater input from modern C4 production that's being produced right there within the Spartina zone relative to the mudflat. So we do see input of autochthonous carbon incorporated at the bulk level. So this is fine, but this is very qualitative. So we want it to be just a little bit more quantitative. So we did a very simple two component mixing model. Okay, so here's the same data set. Okay, we're looking at here's the organic carbon content, and then so we just said, all right, so we're going to assume that any organic carbon sample is made up of 2 components: the background component, which is sort of there in the background, and then there's the excess or the additional component whose concentration can be more variable. Okay, so organic carbon is the sum of these 2 components, the background and the excess. And then we also assume that the C13 value of the background component is sort of uniform. Okay, so we did that be uniform. Okay, so the carbon mass balance, we can say that OC is equal to the background component plus the excess component. And then the C13 mass balance, we can write this as essentially the same exact equation, but each term multiplied by its own C13 signature. So this is a standard way of doing isotope mass balance. So if you take equations 1 and 2, do a little bit of arithmetic, and then eliminate the OCX term and rearrange it, then we get this equation. Okay, and then if you look at this, then it says if you plot the organic carbon content multiplied by its so this is bulk organic carbon content multiplied by its C13 signature, and if you put that plot that in the Y, and then if you plot the organic carbon content in the X, and if you get a straight line, then the slope represents the C13 signature of the excess component. Okay. So if you want to know more about this, Al has a nice, more sophisticated way of showing this for. This is just for 2 components, but you can solve this for n components if you have enough measurements. Okay. So here's what we did. OC content, okay, times its C13 signature. And this is for the Galena Creek, okay, log sediment. So the filled circles are from the Spartina zone, the open circles are from the mudflat, but the regression is only through the Spartina zone. So the slope is, this is a nice, nice relationship. The slope came out to -16 plus -0.8 per mil. So this really sort of screams Spartina with C4. Okay. We did the same for radiocarbon. There's a lot more noise. The p-value is not very good, but the slope is somewhere close to zero. But it's definitely much higher than the bulk sediment signature with -100 to -150. Okay, so based on these findings, so it's autochthonous carbon incorporated into the bulk sediment at Galena Creek. It sure looks like yes. So we did this also for Dunbar Point. We got a different slope, much lower, -16 plus -3 per mil. So this, you might say, well, this looks purely C3, but it could also be, mostly C3 with a little bit of C4. So this is the weakness of C13, just using C3 as the C13 signatures. It can be very inclusive. Radiocarbon values, again, really huge p-value, not very good. This is, you should take this with a big grain of salt. But it does look more positive than the -200 per mil bulk value. So it's unclear, but there's some science for it, but it's unclear for at Dunbar Point. Okay, so to what extent is autochthonous carbon incorporated into the sediment matrix? And do we see evidence for incorporation at the bulk level based on isotope mixing model? Definitely yes at Galena Creek. Dunbar Point, maybe not. We don't know. Can't really see. Okay, so let's look at incorporation into the mineral bound pool. Okay, so we're going to start with bulk sediment. And just to remind you guys, bulk sediment is the stuff that passed the 2 millimeter mesh. Okay, so we took that mud and then we suspended it in heavy liquid. This was sodium polytungstate. And then we centrifuged it, centrifuged it, and collected the material that floated. So we call this FLF for mineral free light fraction. And then we took the pellet and then we resuspended it in the same solution, but this time we sonicated it with a probe sonicator to try and disrupt some of those organomineral, relatively fragile organomineral complexes to see if we can free up some of what some researchers call occluded organic matter. So what floated at that point we call mineral associated light fraction, MLF. And then we took the pellet and then we suspended it this time in much heavier liquid, 2.5 more denser liquid. And then the material that pelleted there we call high density fraction. And then this lumpy brown thing that floated we call mesodensity fraction. And this is the clay-rich fraction. So for all of these isolates, we did carbon content, isotopic values, and I'm going to tell you now that by subjecting sediment through this set of processes, we lost about 30% of the organic carbon that we started off with. So we were only able to tally up about 70% of what we started at the end. And this becomes actually important, so if you could just keep that somewhere in the back of your head. Actually, it's not going to be that important, but it's sort of important. Okay, so I have separate slides for this, but this fraction was by far the dominant in terms of mass and also in terms of carbon. Okay, so this was the biggest fraction, and it's very consistent with what we see in the literature. Okay, so I'm going to show you the isotopic composition. So I'm going to show you what these fractions look like in plots that look like this. So I have organic carbon content on the x-axis, and this is in log scale. Okay, and then first I'm going to show you C13. Okay, and then this is for Galena Creek, and here's the live root data. So live root, very high carbon content, and also high C13 value. So compared to that, here's the So as you can see, detrital material, high carbon content, and then C13 values, so many of them, especially the ones in the spartinazole, cluster around high 14C value as well. So here's the triangle is the free-floating light fraction. So we totally expected these triangles to look more like this. We thought it would be more like detrital material, but it looks, the C13 values are much lower. Okay, and then here's the other let's see the diamonds. This is the other light fraction that we get after sonicating. Again, much more depleted in C13 compared to detritus and the light blue. And then here's the heavy fraction that pelleted, that never floated, very low in carbon content. And then in the middle is the mesodensity fraction, the biggest fraction in terms of mass and also carbon content. So we were not able to find any fraction that looked autochthonous, okay, which was very surprising to us. And then if you see something like a line that kind of the squares are sort of headed towards the root, I'll do a mixing model on this to see if there's autochthonous carbon incorporated into this fraction in a bit. Okay. So we did the same thing for Dumbarton Point. The separation is even more stark. So here's the light root and here's the detrital material and here's everything else. So we really couldn't find no indication of autochthonous carbon concentrated in any density isolates. Like where did it all go? Okay, so radiocarbon values, similar sort of results. So the square is the live root estimate. Okay, so rich in C14 and then rich in organic carbon. All of the others, carbon content varied, but the C14 values were no greater than 100 per mil. So the difference again is 1,000 years. So again, we saw no indication of contemporary carbon concentrated in any density isolate. So this was surprising to us. Oh, sorry, before we go there. So we were a little bit curious about this. The squares seems to be there seems to be a positive relationship between C13 and organic carbon content. So we applied the isotopic, the two-component mixing model to just the squares. And here's what we got for Galenas Creek. So we got a slope of -21 per mil. So maybe it could be like an admixture of some photographs and autochthonous material. C14 -130 plus -60. Again, p-value is not very big. It looks more aged than contemporary. So this was inconclusive. We did the same thing for Dumbarton Point. We got a nice relationship for C13, but this was even more depleted, -25 per mil, and same with the radiocarbon, very noisy, and the slope was very positive. So autochthonous signal, if anything, was even weaker at Dumbarton Point. Okay, so at this point, we're thinking what is going on at the bulk level. We definitely see autochthonous carbon going into the sediment matrix, but once we do the density fractionation, it seems like that autochthonous signal is gone. So, but I told you that we lost 30% of the starting carbon. So we think okay. So a couple of explanations, possible explanations. Autochthonous carbon is spread thin throughout density fractions, so we really can't see it, or it just got lost. It just kind of got washed away during density fractionation. So we think it's this one, and I have some data that suggests that this is the case. And if anyone is curious, I can show the slides later on. But in the interest of time, we're going to skip that. Okay. But this is essentially saying maybe autochthonous carbon, is it more like fragile? It tends to get washed away with a tidal exchange, whatnot. Okay. So if we just recap question number 2, so to what extent is autochthonous carbon incorporated into the sediment matrix? It's unclear how much autochthonous OC is incorporated into the sediments of Dumbarton. The whole signal is very weak. At Galenas Creek, we clearly see this signal at the bulk level, but isotoxinous carbon in the long term. So to cut to the chase, what I'm going to show you, it shows that not nearly as stable as alloxinous carbon. Okay, so we're going to be using the spartinazole validus streak data for C13 and organic carbon content. Okay, and then we're going to do something very similar to the two-component mixing model we did, but we're going to do it slightly more sophisticated manner. We're going to use a diagenetic equation. So we're going to assume OC is again a sum of two components. The non-reactive component, which is similar to the background component, so we're going to use OC and R, and we assume that this is constant with depth. And then some reactive component that we tack onto that, OC sub R. Okay. So at any depth, the total organic carbon is a sum of the non-reactive component and the depth variable reactive component. And so, are we going to fit a diagenetic equation to observe profiles? Can you raise your hand if you work with diagenetic equations? Okay, so you can just forget this phrase. It's essentially a set of equations that so this is, we're assuming that this is steady state. So in other words, if I went back to these sites today and got the same course, we're going to see the exact same pattern. So there's no time variable. Okay, and we say that so the diagenetic equation, you can write all sorts of different types of equations, but in sediments we generally consider if they're macrofauna like crabs and worms and things that's mixing things up, we put in what's called a bioturbation or mixing component. So there's organisms that's stirring up the mud at what rate, and this D sub E is what's called a biodiffusion coefficient. So bigger this is, it means that the worms are doing more activity. And then there's the burial component. So everything is like sedimenting. So there's the speed at which sediment is buried. Omega is the mass accumulation. And then there's some reactions. So there's respiration, chemical reactions, whatnot that's going on. And we assume it's first order. And K is the reaction rate constant. And again, we assume it's steady state. Okay, it's the simplest way to go. Simplest place to start. Okay, so this is probably one of the easiest or the simplest diagenetic equation one can write. And because of that, there's also an analytical solution which looks like this. Okay, and the point here, and then this is for carbon. We're writing an equation for carbon which will fit this one. Okay, but we can link the carbon equation to the C13 equation. So this is about C13 to 12 ratio in organic carbon. So these two are linked, so we can mathematically link them as well. So we can rewrite an equation like this, but with C13, and then the only difference is that we have this lowercase r, and this is a 13 to 12 ratio. Okay. So, what I want to show you is the orange ones are the fitting parameters. In other words, I fit the model to the data by tweaking these. So you find the best fit by tweaking these values, and then see what we get. Okay. So it's the degradation rate constant, the reactive carbon content at the quartile, and then the non-reactive carbon component, and then the isotopic value of the reactive and the non-reactive fractions. And then these blue ones, the biodiffusion coefficient and omega, I estimated from literature values. Actually, I wasn't able to find a good biodiffusion coefficient, biodiffusion coefficient for San Francisco Bay. So I went to the literature, I looked for similar sites, and found the smallest one, biggest one, and I tried both. And the point is, and I found that the outcome is the same. It didn't really make a difference. I'll show you the smallest version. Okay. So here's the result. So the red lines are the actual data, and then the blue line right here, that's the model fit. So this is really like almost like a straight line. So it's one of the easier things to model, I guess. So then this is the non-reactive component, and this is the reactive component. And here's the total C13 value of the organic carbon. Here's the C13 value of the non-reactive component. So if I summarize C13 signature of the reactive component is minus 16 per mil, which is very similar to, very similar to what we got using a very simple two-component mixing. So I think there's some internal consistency here, which is nice. And then the C13 signature of the non-reactive, this guy, is minus 28 per mil, which looks more like C3. And then the degradation rate constant, I'm sure this means, I don't keep these values in my head, but I know I looked it up, and this is like reasonable for, comparable to say like coastal marine sediments. And I also tried doing this with a diffusion by diffusion coefficient. So this is for 10 centimeters per year, which is on the lower side. I increased this by tenfold to 100 centimeters per year. You get exactly the same, essentially the same C13 signatures. It's just that the K value increases by another factor. So that's the only difference. Okay, so it looks like the reactive component is known by 50 centimeters depth, and it looks very much like autochthonous carbon. Okay, so majority of autochthonous OC does not survive long-term burial. Okay, exported as bicarbonate, is it oxidized, or does it just dissolve into dissolved organics and then get washed away? So it looks like these salt marshes are repositories of mostly aged allochthonous imported material. Okay, so I'm going to summarize, wrap up. So what supplies OC to these sediments? Organic detritus definitely comes from local plants, but this is not the major component of the sediment OC stock. We found quite a bit of it, but it definitely was not the major component. And allochthonous carbon that aged before reaching the marsh seemed to be the major component. And then to what extent is autochthonous carbon incorporated into the sediment matrix? There's clear evidence of incorporation in Galenas Creek sediments, but it's unclear whether it's incorporated into the mineral boundary. We really couldn't see it. So we're just wondering, is autochthonous carbon more prone to being like washed away? There's science for autochthonous OC incorporation overall in down-bottom point sediments, but it's very weak, very weak. How stable is autochthonous carbon in the long term? Not really stable compared to imported allochthonous carbon. So at Galenas Creek, Portop is about 50%. It's 50-50 imported local, but at the base of the core, allochthonous carbon dominates. So organic carbon accretion at these sites appears largely decoupled from ongoing anthropogenic CO2 emissions. So implications and further questions. So blue carbon accounting requires much more than just measuring bulk carbon stocks and burial rates, which is how it started. It's getting a little bit more, there's more nuance now, but the initial publications were people would measure quantum carbon, and somebody had measured burial rates, and they're like, wow, we have a number. That's how much the site is sucking up CO2 from the air. And that really bothered me. So that's why I did this. Okay. And then I'm overestimating the ability of tidal marshes to offset CO2 emissions. So while we were working up the data, this paper came out from in Holland. I can't remember. So similar. Sorry. Okay. Thank you. Thank you. Shelt. Is that the right? Okay. So Shelt estuary. So very similar conclusions. They also use radiocarbon, different approach. But essentially the same takeaway. But as far as I know, it's only this paper and our paper that really talk about this issue. And a colleague of mine sent me a paper that he said he liked, and I read it, and it again makes the assumption that imported organic carbon is recently photosynthesized, which is again probably not true, and this is a sort of random thing now, but there's actually a lot of data for, so we talked about cesta, so particles floating in rivers and estuaries, so if you measure radiocarbon values for those particles, they're not that new, they're pretty old. So there's definitely more work needed so that there's more data out there so that people can be more aware of the fact that these sites are a little bit more complicated than we think. So one other thing that's interesting is how important is natural export of carbon out Saltmarshes, how do we or can we trace the fate? So if you don't mind, if I go back. So I didn't really talk about this, but so this is being lost. The reactive component is being lost. So the assumption is that this is all turning into carbon dioxide, but that's probably not the case. So if you oxidize organic carbon under anoxic conditions, it turns into bicarbonate, which is an ion. So it can go sideways. It's getting a little off. So there's a lot of interest in that now, and I think there's more room for research along those lines. Okay, so thank you for your attention. Yes.
Thank you. This is pretty new to me, so maybe this is a really lousy question, and I'm a geologist. But